Okay, let's start the exercises now. For section what, 7? Yeah. So Q is countable. That's what you have to show. Okay, so first we have to show that Z, not Z plus Z, cross Z is countable and that there is a surjective map from this to this. Then we'll be done, right? Now Z is countable because it's shown in the book and I'm not elaborating on that. And a countable product or sorry, a finite product of countable sets is countable and fine 2 is definitely finite. So Z cross Z is countable. Yeah. So what does that mean? That means we just have to find the surjective map. And that's simple. We just take M by N. So this is surjective because every rational number is defined this way, except if it's minus minus and it cancels out. So it's a surjective map. And that's what we need. So is that it? Yeah. So to check if the surjection, I'll just be a little bit clearer here. Yeah. So take any rational number. There are four, I believe, pairs that give you the answer, or two. Yeah, it's two. If it's positive, then it's minus m comma n. If it's negative, it's minus m comma n and minus plus m comma minus n and m comma n and minus m comma minus n. So we'll get two pairs for the positive ones and two pairs for the negative ones, and yeah, essentially it's a bijection with q cross 2 if you want. Yeah. So this is a surjective map, and because of that, we're done. Yeah. Okay. Yes, showing that these maps are bijection. Let's go. So this was the proof that Z plus cross Z plus is by is countable. Yeah. And what do we need? We need a bijection with Z plus. Yeah. So first, yeah, Z is for the record bijective with Z plus by 2n and 2n minus 1. Yeah. So if it's 1, it goes to 1. If it's 2, it goes to 4. And yeah. So if it's, I think it's flipped, I forgot. Oh, it's a matter of negative and positive. Yeah. So essentially, put one of the copies in the even ones and put one of the copies of Z plus in the odd ones. And 0 happens to be somewhere in there. I think 0 is in 0. Yeah. Something like that. Okay. For Z plus cross Z plus, let's go with this. Okay. So A is the set of pairs x comma y, where y is less than equal to x, and we have a bijection from z plus to cross z plus to a f, right? And what was it defined as? X minus 1, x plus y minus 1, comma y, right? Yeah, hang on. Oh yeah, okay. Yeah, so it's still in, it's a subset of z plus cross z plus. Yeah. Okay, now how do we show that every single ordered pair is covered here? So, well, every single y coordinate is covered here, right? So let's just take an arbitrary n comma n, right? We have to show it's surjective and injective. Let's start with surjectivity. So an arbitrary n comma n. So y is equal to n, right? And x plus n minus 1 is equal to m, right? So there exists a unique x that satisfies this equation. So by uniqueness, we get yeah. Actually, yeah, the uniqueness, there's a unique y that's equal to n, and there's a unique x that's equal to m minus n plus 1. So injectivity is proved that way. And surjectivity, well, we got a y for this n and we got an x for this equation. So yeah, this one is easy. The other one is slightly harder. Okay, now we have a map from A, which is that set, to z plus. And it was defined as g of x comma y goes to, yeah, half x, x minus 1 plus y, right? And keep in mind y is less than or equal to x, right? Okay, so plug this in here, right? What do we get? We get this entire expression is, well, y is a subset of z plus, right? So greater than or equal to 0, plug it in here. We get this entire expression is greater than or equal to half x, x minus 1. And hang on. Oh, yeah, 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 strictly greater. And less than equal to half x plus 1, x minus 1. Sorry. Yeah. Just plug in x here. What do you get? Figure it out, right? It's the same thing. So what does that mean? That means essentially you go for all values of x in between and then you cover it. So how do you show it's injective? Well, no, this is easier. Yeah. Which is easier? Let's see. So surjectivity, yeah, choose the integer that is least or greater. We'll figure that out. We can use either, given that we've proven the maximal element thing in the integer section. So choose the greatest integer that is less than this thing, right? Yeah. Choose the greatest integer that is less than the number you want to get for surjectivity. So let's call it m, right? So there has to be a greatest x. Now, yeah. Now we have to choose a y less than equal to x. Now m has to be less than equal to this because otherwise it will contradict the greatestness of x. So choose the unique y since m is an integer. Choose the unique y such that essentially this is also an integer. Keep in mind because so this is actually even, right? It's easy to show that x squared minus 1 is even, x squared minus x. You show it, I am not proving this. You show it by, okay, I'm proving this fine. You show it by assuming x is equal to n plus 1 if it's odd, and then you show it goes all the way down to some 2n, right? And if it's even, then it's even, right? You can just take the two common out. So because it's even, it's going to be an integer, right? Yeah. So this is an integer, this is an integer, and this is an integer. So by something of y, I think I've proven the property. I'm not sure which property it was. You can choose the y to get the m. That's the point. And yeah, that shows surjectivity. And for injectivity, well, if they're equal, so let's see. So if x is not equal, then they're not going to be in the same range essentially, right? They're going to be in another half, right? In another segment. So no matter what y you choose, given the other segment, it's not going to ever overlap, right? Now, if the x's happen to be equal, then the y being different will ensure that for the same x, essentially m plus y is not equal to m plus y prime if y and y prime are not equal. The cancellation law will stay. So injectivity is fine here too. Yeah. And if both aren't, so yeah, if x is not equal, then it's done. And if y are not equal and x is equal, then yeah. And for surjectivity, just to recap, yeah, you can pick the unique y. For the sake of completeness, I'm going to check what property it was. Uh, Yeah, I think we're just taking the every non-empty set that's bounded above has the largest element thing. So it is bounded above and it will have the largest element. For M, yeah, yeah, it works out. Okay. You can use proof by contradiction. There are details hidden there, but I am not going to. So yeah, that's how you show that this is bijective, essentially. Yeah. This was slightly harder for me because of the bracket thing, so I couldn't figure out that part. It took me a while there. Okay, show that there's a bijective. Oh, I haven't discussed this then, have I? Power set of z plus and x to the power omega. And essentially, yeah, there's the characteristic set. So any subset of z plus, it's going to have or not have it at a particular position, right? So let's see. Take a subset of z plus and f of, and we have to map it to a function, right? So let's call it g, that's belonging in the set. And g of n is equal to 1 if n belongs to a, and 0 if n doesn't belong to a. And you can see it's a bijection because if the sets are equal, sorry, if the sets are unequal, then they have to differ at least one place, and that will lead to a different function. So that means it's injective, and it's surjective because for any sequence of ones and zeros, you can make a set of integers. So yeah, yes. Show that the algebraic numbers are countable. That should be simple. So hang on. Does it require choice now? Maybe. Okay. Yeah, let's see. Okay, so essentially, we can get, so for each okay. Oh, okay, okay. They're countable set technically, but okay, yeah. So let's find, okay. So take all the roots of all the polynomials of degree n, right? Right. So for each cardinality n, we'll get a certain amount of roots, right? So for degree one, we'll get a certain amount of, we'll get a countable amount of algebraic numbers because the parameters that are the coefficients, they're countable in number because they're going to be rational or integers, right? Yeah, rational coefficients, right? So they're going to be countable. Now, so for each n, they're going to be countable because a finite product of countable numbers is countable, right? So we get n times n many countable rationals, right? And you take the union of all of them. So each, yeah, question three. Okay, let's go. So we're assuming every single polynomial equation, is it zero or zero, has finitely many roots. Fundamental theorem of algebra. We're not proving it here. Yeah. So given that, uh, yeah. So we just have to show that there is a countable number of polynomial equations. Then what does that mean? That means a countable. Yeah. So if we show that there are a countable number of polynomial equations, right, of degree n. let's say, right? So an, degree n. Uh, so that will be a finite number. Let's call it m. And yeah, for each degree n, we'll have that. So their union is going to be countable, right? So we just need to show that there are a countable number of polynomial equations for each degree, right? And because this is finite. So finite times countable is countable times countable, and therefore is countable. And this will be countable assuming a certain axiom. Uh, yeah. So I'm not sure if this is true without a certain axiom too. Yeah. So now we have to show that this is countable. For that, well, how many choices of A naught do we have? We have q many, right? Rational numbers, and that's countable. So this is the same cardinality or the same amount as q times n, which is the same amount as q. Or at the very least, it's countable, right? This is countable, this is countable, this is countable. So yeah, countable, 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 countable. So these are all the algebraic numbers, right? Yeah, it's all countable. I'm not sure if the countable implies countable is true for this case or not. I'll have to check that. Yeah. So transcendental. Yeah. Okay. So assuming the real numbers to be uncountable, uh, the real numbers by definition is equal to the union of the transcendental numbers and the algebraic numbers, right? Uh, yeah. So what does that mean? That means since the algebraic numbers are countable, assuming towards the contradiction, the transcendental numbers are countable, a finite a countable that's also finite union of two countable sets is countable, and therefore the real numbers are countable, and that's a contradiction. So no, the transcendental numbers are not countable, and there are plenty of examples of transcendental numbers besides V and pi. One example is essentially 0.01, then two zeros and one, three zeros and one, and four zeros and one. I hope that's transcendental. I hope it is. I'm not entirely sure now, to be honest, but I think it is. Yeah. So you just go on, right? The pattern. And yeah. Hmm. Okay. The set of all functions from 2, 0, comma 1 to z. So yeah, let's see. Let's see. So each function is going to be what? Let's see. Yeah. Essentially, this will be z choose 2. Like the intuition is it's omega. So omega is kind of z plus. Omega choose 2 is equal to omega into omega minus 1 by 2, which is equal to almost omega cross omega, which is almost equal to omega, which is z plus. So that's the intuition. And to show it properly, we just need to construct a surjective function, right? Yeah. So z cross z might describe it. Yeah. So z cross z, the first one is f of, yeah. So there's a surjective function from z cross z to f. What is that? This m comma n maps to f of essentially m comma n, right? The first coordinate goes to m and and the second coordinate goes to n. And this is a surjective function because it doesn't necessarily mean that we're going to get a function every time. But yeah, since z cross z is countable and is surjective, therefore it's countable. So yeah, the set of all finite. Yeah, so the same thing can be extended to Bn. Essentially, since a finite amount of uh, z plus products are still countable, and we got a surjective function again. And since the countable union of countable sets is countable, this is also countable, right? Yeah. The set of all functions from z plus to z plus is uncountable, I believe. That's because the diagonalization argument still holds. So yeah, I'll just show that the set of all functions from z plus to 0, comma 1. Sorry, hang on. So if I show that there is an injection from this set to this set, then what do I get? I get that um, after composing the injections, I can get that this is uncountable and therefore this is uncountable. We can use a contradiction, right? I'm not going into that detail, but essentially I'm just going to show that this set injects into this set. Yeah. So, well, but yeah, any function that goes from z plus to 0, comma 1 is also a function that goes from z plus to 0, the integers, since 0 and 1 are integers. So we've got the trivial injection. So this is certainly of greater cardinality, and that doesn't help anything. The point is, okay, no, yeah. So this is essentially x to the power 9, right? This is the same thing. Yeah. So E part and the set E actually, the set E is x to the power omega, essentially. It is x to the power omega. And this injects into D, right? So there is no injection from Z plus to x to the power omega, right? Uh, so a subset of an uncountable. Yeah. Yeah, sorry, I'll just start again. Okay. So towards a contradiction, let there exist a surjective function from Z plus to the set of set D, right? Okay. Now it's clear that there exists an injective function from E to D, right? Okay. So this is let's call it bijective, doesn't matter since we're assuming D to be countable. It's infinite for sure because we can, well, yeah, I'll just write the identity functions. No. So for we can get a function that gives out every integer. That's at least countably infinite, right? That makes the injective map from the set of integers to the set of all functions, the set D. So it's at least countably infinite from that. Mm, yeah, so I'm kind of skipping this one because later on I'll prove that they have the same cardinality, D and E, which means they have a bijection, and that will automatically show that Z plus cannot they cannot be a surjective from Z plus to D, because otherwise we'll have a projection from Z plus to E. So yeah. Okay, set of all functions that are eventually zero. Yeah. So this yeah, so let's fix the n, right? So let's say it's eventually zero from n onwards, right? So for each n, we're going to get a finite amount of functions, right? Yeah, I'm just going to write it from Z plus to Z plus, right? The set of all functions from Z plus to Z plus that are eventually constant. They are what? These are countable, and because of that, every other part above it is going to be on, right? So the functions that are eventually constant. Yeah. So for each constant m and for each position n, there are going to be a finite amount of functions, right? And then yeah, you just get z plus cross z plus, and you change that, so you'll get a countable set, right? So there's a surjection from z plus cross z plus cross z plus to be safe because of the finite amount of functions we get, right? And because of that, the set of all functions from z plus to z plus that are eventually constant are countable. And then you extend it to 0, comma 1. So we'll just get a simple injection, and for eventually 1 is the same thing. We just remove this 1m to finite. So it's yeah, we get an injection that way, or surjection. Yeah, they were surjections the whole time. Sorry. Hmm. So in general, if we have a surjection from A to B and A is countable, then since A is in bijective correspondence with Z plus, there's a surjection from Z plus to B, and therefore B is countable. And you can extend it back in another way. Yeah. So I'm directly skipping to I now, and the set I of all two element subsets of Z plus. Two element subsets. What does that mean? Yeah, so that's also, I believe there's a surjective function from Z plus to Z plus 2. Hang on, isn't this the exact same as, yeah, almost the same as the set of all functions from 0, comma 1 to Z plus. The difference here is that there's a surjection from that set to this set, to the set I, right? So there's going to be a two set, and that's going to correspond to an injective function. So the set of all functions is going to be surjective on it, right? Okay. For J, set of all finite, so yeah, you just change this to a finite. We're getting the same thing. Yeah. Okay, Schroeder-Bernstein theorem. So yeah, so I took far too long to solve Schroeder-Bernstein theorem and prove Schroeder-Bernstein theorem. And yeah, I solved part A. There was no problem with part A, but with part B, I was going about it all wrong, and I cheated. So I looked up the solution, and well, I have the solution and I'll present it. But yeah, okay, so I'll solve part A2 now. I mean, I've probably done it, but I won't include that part in the videos. Yeah. Okay. So we have B is a subset of A, and there's an injective function from A to B, right? And we have to show, so A is a superset of B, and f of A is a subset of B because the image set has to be contained, and f of B is contained in f of A because the inclusion is transferred over image sets, right? And by induction, because inclusion is transferred, you can check that if you define this to be A1. So, and f of A1 n is equal to f of an plus 1. Sorry, yeah, an plus 1. Then you'll see that you'll get this trend. And essentially, the proof of it is exactly that. The image sets are contained, right? So we're taking the image set, and since an is contained over bn minus 1, bn is containing an plus 1, right? We're just taking image sets. So that's how we follow along with the proof. Now, we define a bijective function h, which is using f of x if there exists an n, x belongs to an minus bn, and x otherwise. Okay. Now, yeah, now we have to show that this is a surjective function. Okay. Now, you have to see that by definition, both of these sets, they'll combine to make A, essentially, right? And if x belongs to A1 minus B1, then, well, f of x is going to belong to A2 minus B2 because essentially the image set transfers. We also proved it in section 2 of functions, right? So we proved that. Now, and that by definition is equal. So yeah, okay. Now because of that, so union of this, excluding this one, and the otherwise part is going to make B because this entire part and otherwise is going to make A, right? So yeah, that's the best way I can explain it. But the point is, yeah, it's the whole set, and this is a bijective function over this category, so we just have to worry about it being bijective here, right? And for injectivity overall, we have to make sure that the functions don't interfere with each other, right? So identity function won't interfere. We just have to make sure this never ends up in this set. But that's true because of the image set thing again. So because of this, if it's true for A1 and B some n, then it's going to be true for some n plus 1 too, right? Because of f of x. So injectivity is trivial. For surjectivity, again, you just use the same image set principle. So if, let's say, the output y is in, well, let's see. So there has to exist some n, right? So it's in, let's say, am minus bm. Then x belonging to am minus 1 minus bm minus 1 is going, there has to be such an x such that y is in this set and it's equal to f of x. Why? Because by definition of what am and bm represent. So yeah, that's how we get a bijective function from this situation. And now from this is where I cheated. Okay, so f is an injection from A to C, g is an injective function from C to A. Now fog is going to be an injective function because we proved it for compositions, and it's going to go from C to f of A, right? And h is, and I'm going to call it h, right? So h is an injective function because of composition of functions. Now, yeah, and observe that f of A is the subset of C. So by the A part, there's going to be a bijective function from M, we'll call it M, from f of a to c, and this is a bijective function, right? Now, by definition, sorry, I'm going to call it f prime now, from a to f of a is a surjective function if f prime of a is equal to f of a, right? It's a kind of opposite restriction, but we can't really define that, so that's why. Now, f prime of a is a surjective function and an injective function because f is an injective function. So what do we get? Well, f prime is a bijection from a to f of a, m is a bijection from f of a to c, and therefore there exists a bijection m composed with f prime that's a bijection from a to c. And yeah, so I was stuck on the problem because I was trying to do it from scratch and I didn't use the party at all. I didn't know we had to use that. I mean, I thought it was a motivation. But yeah, so Schoder-Bernstein theorem. Okay, yeah. So now that we've shown proven Schoder-Bernstein theorem, for to show that any two sets have the same cardinality, we just have to show that one of them has an injective function. There exists an injective function from one to the other, and vice versa, right? And this is also it also means to have a greater cardinality for a similar reason. So sorry, yeah. And this notation makes sense because both of these combined imply A is equal to C, which is exactly what it means to have the same cardinality. So yeah, this definition is introduced later. Okay, so how do we show that the set D and E have the same cardinality? So I'm going to notate D, I believe, as omega to the power omega and E as 2 to the power omega. And essentially, this is all the set of all functions from Z plus to Z plus, the set of all functions. Yeah. Okay. Now, first, I'll show that I'll put an intermediate step uh, here. Now, I'll explain what this means, but essentially, it's the set of all functions from omega integers to the set of all functions from integers to 2, right? And then I'll later show that this is the same as, and then this is the same as, right? Essentially, this is the idea. Now, we'll give meaning to these words eventually. Not omega itself, that's theoretic, but the idea of the proof at least. Now, yeah, so we take a function from z plus to 2, right? Okay. Now we need for this an integer, right? Or for every function, for every integer, we need a function from, sorry, yeah, for every integer, we need a function from z plus 2, right? That's very simple. You just take for every integer the function that is only one at that very integer. So essentially a kind of characteristic function. And that will be an integer injective function from omega, the set of all, yeah, to this, right? Okay, so what does that mean? That means let's say we take the number 37, right? So we'll have the function that is 1 at n is equal to 37 and 0 otherwise. And that's the injective map. So this one's done. And essentially what's going to happen is, well, oh yeah, that's one direction. And note that 2 to the power omega is, there's a trivial injective map from 2 to the power omega to omega to the power omega. And that's, well, you just put 0 everywhere else, right? So that's a trivial map. You can just map it directly. And because of that, we do know at least that there's an injective function from 2 to the power omega to omega to the power. But yeah, do note, what the notation is. Yeah. Okay. Now for this one. Well, for any arbitrary function, so we have a function from z cross z to 2, right? And here we have a function from z plus to a function. Yeah, yeah, a function that's z plus 2. And the idea is that we can define the composition to be a new function. So like it goes in a matrix kind of thing. So you can arrange both of these in a matrix, and these are actually the same cardinality. I mean, all of them are, but yeah. So let's say it's 0 here, and the value at essentially the value at this and this will be the value at this and this, right? So I'm going to index them by G1 like that, and then we have 1. So this is the val. This basically would correspond to the value of G3 for G1, value of 3 for G3, and so on, right? So that's how we can arrange it in a matrix. And from this picture, it's very clear how there's a bijective correspondence between the two, right? So yeah, I'm not writing it explicitly, but essentially, actually, I'll write it. It's not that hard. So G of M, and we take F of N. So yeah, F of N will be a function, and then we take its value at M, right? And that's equal to F of N comma N, essentially, or N M comma N, doesn't matter. Yeah, and from that we've gotten a bijective correspondence actually. Now for this one, uh, well, let's see. Yeah, you'll have to go along a diagonal path. Essentially, that's one way, but essentially there is a bijective correspondence from z plus cross z plus and z plus, right? So you just take your favorite bijective correspondence and you compose them. And what do you get? You get a function from z plus to 2. And from your favorite bijective correspondence, you can get any map you want. You might have to invert this. Yeah. So F inverse, sorry, G inverse, and composed with F, or vice versa, I forgot. And then you'll get a function from z plus to 2. And you can check that it's an injective map at the very least. This might also be bijective actually, because yeah, I'm taking the bijective correspondence, but if you want, you can take the injective correspondence of one which you need, the prime one, which was an example, right? Yeah. From Schroeder-Bernstein theorem, it's also trivial that these have the same cardinality because of the prime injective function and the trivial injective function. Here you just map it to 1 comma n, and then you'll get 1. So yeah. Yeah, that theorem is quite powerful, and yeah, we'll be using it a lot. So because of that, we get both inequalities. And from that, we got an injective map from composing from omega to the omega to 2 to the power omega, and yeah. So that's how we prove it. And that's why I wasn't discussing it in that part. And of course, then everything in between has the same cardinality. And that means all decimal expansions of the real numbers can be mapped this way. And it makes sense because if you take all the numbers from 0, 1, which we'll know is the same uh, size as the real numbers, you can expand it in decimal form, like you already know, whatever. And you can also expand it in binary form. And essentially, you'll be multiplying it with 2 to the power minus n for each digit. And you'll get a unique number for each decimal expansion and binary expansion. And that's why these both have the same cardinality. So size is essentially defined with bijections and injections. Okay, countable subsets of, yeah. So yeah, so realize that we've also actually accidentally solved question 8 by showing, well, so what is the set of all countable subsets of real numbers? I don't know how to write it, but at the very least, we can say there's a bijective correspondence with the set of all functions from integers to 2 to the power omega, which I'm going to call, okay, x to the power omega. Fine. That and 2 are the same thing. It's quite convenient to write so. So this is the exact same thing as the set of all count. The set of all these functions is the same thing as the set of all countable subsets of the real numbers, right? So, well, this can be written notationally as this, right? In fact, it's the exact same thing. And I already showed that this has the same cardinality as 2 to the power omega cross omega and, 2 to the power omega, and 2 is x, right? So I've already shown this, and the other way is trivial. You just take the function that's the any one element for each. So for the other map, you just take the function that maps every integer to one element, and you'll have these many functions, and that's it. So yeah, they have the same cardinality too. Okay. Okay. Yeah. So we have H1 and H2 defined for the transfinite. Sorry, not transfinite yet. The recursive definition thing. Okay. Yeah. People confuse this as 4 in my experience for some reason. Yeah. So H1 is 1. H2 is what, 2? Yeah. And H of n plus 1 whole square. There's no whole square yet. Is that it? Yeah. So let's see. So how can we define H of n plus 1 in terms of the previous? It's kind of a spoiler, but essentially we need to get H of n plus 1 in terms of its predecessors, and it must be defined unique. So the thing is, we can't define it uniquely here, but yeah. So yeah, okay. I'm using algebra here, but so this is something, right? And I'm using, yeah. So from manipulation, we get h of n plus 1 is equal to h of n minus 1 square plus minus, yeah, root hn whole square root, right? Yeah. And you can see there are, yeah. So we need to make it such that there can be, so first of all, can it can it be minus? Is there a problem if it ends up being minus? Let's see. So hmm, h of 3, right? H of 3 is going to be h of uh, 2 whole square, so 4, and there is plus and minus 1, right? So plus minus 1 essentially. So one of them. We're deciding which to pick for now. Yeah. Hang on, are you sure there was a square? Oh, my bad, my bad. Yeah, there was no square here. So that means there's no here, nothing here. Yeah, nothing here. It's just plus, and here's the plus minus. Yeah. In that case, we only have root 5. No, yeah, root 5. Okay. But again, it can be plus or minus, and that's the problem. So with uh, hmm, wait, I messed it up, didn't I? Yeah, I did. It's going to be, hang on. Okay, so the principle of transfinite recursion says that recursive definition says that H1 must be defined uniquely and Hi must be defined uniquely in terms of the previous values, right? Yeah. So, yes, H of 1 is 1, H of 2 is 2, H of n plus 1 square plus H of n minus 1 square, sorry, minus, yeah, is equal to H of n. So H of n plus 1 square is equal to H of n plus H square of n minus 1, right? Okay. Now the problem is there are two values for which such an H of n plus 1 square is equal to this, right? So in 3's case, H of 3, it can be equal to plus or minus root 5, right? Uh, just checking. Or is it root 3? 1, 2, yeah, 3. So because of that, it's not unique, and that's the problem. And to define it uniquely, we simply take only the positive one. So we can put it as, so if we define h of h plus n plus 1 as square root of plus hn, what we're forcing here is that it's going to be positive. And because of that, it's a unique value every time. The square root we've shown to be unique. But we haven't shown that there's a unique number such that the square is that. We've only shown it's unique if it's positive. So yeah. Uh-huh. So that the formula of part A does not determine it uniquely done. So I just reformulated it. Oh, it doesn't determine it uniquely. Yeah. So I've shown one possible H, but another possible H is taking the negative one. Actually, no, not the negative one, because so if we take the negative one, the problem is that the value could change a bit too much, and it could be so negative maybe that would it? Maybe not. Yeah, let's see. So suppose instead of plus root 3, we take minus root 3, right? What would happen? Right. Now H4 will be, now again, we're free to take plus or minus because of the formula. So it would be minus root 3 plus, hmm, that was 2, right? So 4. Yeah. I'm actually just trying to follow the hint. Otherwise, I would have used something else. So f of 3 is equal to minus of h of 3. That's fine. But how do we ensure that f of I is equal to h of I for the remaining? So for that, hmm, well, okay, I think by I is not equal to 3, it wants to say that, it's, yeah, it's for 1 and 2. Okay, so h of 4 is a unique one. We can take positive from now on. Can we do that? Hmm, h of 5 will be square root of this thing square now, right? So that would be 3 minus, no, plus square root of something, some positive number. And the point is it stays positive from now on. So, yeah. Okay, so now, this was f the whole time. Okay, now f is definitely not equal to h because it's differing at one value, and at least, and yeah, it satisfies the property by the principle of finite. Okay, it does not. It satisfies the property star, but it's not unique. Like it's taking the other alternative we could take. Yeah, that's the best I can show. Like that's the closest thing there is to showing. Okay, yeah. So to show that there is no function, we just have to arrive at a contradiction. So for C part, fine. But yeah, I write it this way. Like if you can cross it over, then it's a 4, but otherwise it's 9. Yeah. Okay. H of 1 is 1. H of 2 is 2. And H of n is equal to H of n plus 1 square plus H of n minus 1 square. Yeah. So H of n plus 1 is equal to H square n minus 1 minus H of n root. Right. Now we have to show that there is no such function. Okay. So let's see. H of 3 will be equal to 1 minus 4. Right. Actually, yeah. Sorry. So let's just remove it. H square of 3 is equal to 1 minus 4 is equal to minus 3. And the point is that there is no number, for every real number, x square is greater than 0, which is a contradiction here, since minus 3 is less than 0. So yeah, because of this contradiction, we cannot get a function from z plus 2r that is sort of satisfying this formula. And yeah, we're done with the